circulating. And in 1970s, the quark model became popular, and that is the model that remains popular to this day. And so when I was presenting some aspects of my concept previously to project colleagues, some people told me that there's a difficulty to concentrate on my experimental data because the quark theory is so good. So now in my presentation, I will focus on experimental data, but to get the right motivation, I have a few slides about the assumptions behind the quark theory, which I will quickly go through. So the basic assumption behind the quark theory is that both proton and neutron each comprise 3 fractionally charged quarks, but these quarks are always observed in the bound state. So in that way, quark proponents tell experimentalists, don't bother looking for quarks, you don't find them. Okay, so how do they think then quarks exist? The idea is that they can be seen in high-energy proton-electron collision experiments. These are called deep inelastic scattering in the physics language. And the idea of these experiments is the hypothesis that if the electron flies energetically enough into a proton, then it will scatter not off of the whole proton, but only from a subparticle of the proton. So to construct the statistics of these subparticle scatterings, experimentalists use the so-called F2 function, which maps the statistics of the momentum exchange as a function of the mass fraction of the particle. So here the x is the proton's mass fraction. And there you can see on the chart the original F2 data that has not been adjusted in any way. So Gell-Mann's prediction was that the peak must be at x equals 1/3, which corresponds to 3 subparticles. And what you can very easily see is that Gell-Mann's prediction is wrong. So this mismatch between prediction and experiment then necessitated a second assumption. And the second assumption is that there are not only 3 quarks, but also there is a sea of virtual quarks and gluons, and those cause this mismatch. And after fitting all the parameters, quark proponents suggest that the actual mass of the quark is only 2 to 3 megaelectron volts, so very small fraction of the proton. Okay, then we have these 2-3 megaelectron volt point-like quarks, and we can calculate their magnetic moment with a well-known formula for the magnetic moment calculation that you can see there. And then you get a mismatch of a factor of 100 with respect to the proton's magnetic moment. Okay, so then that initiated another assumption that quarks have 2 types of masses. So one mass is the naked mass that you see in the inelastic collisions, and the other mass is the so-called effective mass. And this effective mass is about 340 megaelectron volt that is showing up in the magnetic moment measurements. Okay, so then we have this effective mass. So we take 2 such quarks and form a pion, for example. Then the pion mass must be about 700 megaelectron volts. Okay, so now we again have a mismatch by a factor of 5 with respect to experiments. So we need yet another assumption that these effective quark masses are very particle specific. So in every particle you have a different type of quark mass. Okay, so we have these quarks with highly variable mass, that 3 of them are moving around in a proton or neutron, and they always result in a constant magnetic moment. So why is the magnetic moment constant? Why is it not adding up with different vector angles? So then there is yet another assumption, fourth assumption, that actually it's already assumption number 5, that the 3 quark spins are isotropically correlated. It means that they're always aligned in the same direction. Okay, sounds logical assumption, but it was pointed out to quark proponents already in the 1960s that this assumption seems to violate the Heisenberg uncertainty principle. And to get around that, Oskar Greenberg introduced yet another assumption that quarks have also so-called color charge. And again, they told experimentalists don't bother measuring it, we will never measure it, but the color charge is there, and then that removes this problem with the Pauli exclusion. Okay, so does it really work? Does this color charge assumption remove the contradiction? So I recently published a book with some co-authors, some of whom are in this room. And in this book, we dedicate one chapter to the analysis of Pauli exclusion principle. It was written by Paul O'Hara. And Paul O'Hara's derives mathematically that three particles can never be in isotropic spin correlation, because that leads to a mathematical contradiction. And his proof is actually quite straightforward. It's less than 2 pages, so I can send it to anybody who is interested to read it. And what this means is that there is still a contradiction with Pauli exclusion principle regardless of the presence or absence of color charges. Okay, so we have this long stack of assumptions that finally lead to a mathematical contradiction. I think rather at the end, because otherwise we get into long discussions. Okay, now let's see what the quark theory says about the neutrons. So according to the quark model, neutron decay starts by the ejection of an 80 gigaelectron volt particle that is 80 times heavier than the neutron itself. So that's quite a magic trick. It's like magician pulling out an elephant from the hat. And but there is no experimental evidence for this assumption either, which means that these 80 gigaelectron volt particles have never been observed in neutron decays. Moreover, what is important to realize is that there is experimental counter evidence. So let's consider an interesting isotope, the decay of dysprosium-163. So this is stable as a neutral atom, but when it's stripped of all of the electrons, then it becomes a beta decay isotope. So now let's start with this stripped dysprosium-163. So it is beta decaying, which means according to the quark model that it produces these 80 gigaelectron volt particles. And according to the theory, the production of this 80 gigaelectron volt particle is completely independent from the electromagnetic environment. I should not care about the presence of orbital electrons. But if we add orbital electrons, then we can see that the beta decay stops. So it means that actually the electric voltage is the control parameter. And this is, again, a contradiction with the theory. So this clearly shows that there cannot be any 80 gigaelectron volt particles produced in this process. Okay, so after this very quick theory overview, I hope that everybody is finally interested in and has motivation to look at the experimental data. So now I will focus on the experimental data after these motivating slides. So one very big set of experimental data is the map of nuclear isotopes, where with each isotope it has been mapped out what happens to them eventually. So in this map, it's like a periodic table of isotopes. On the vertical chart, you can see the charge number. And on the horizontal slide, you can see the difference between the charge number and the mass. So in this map of isotopes, you see in the middle this black line, that is the line of stability. These are the stable isotopes. And what you can see is that if we move from any direction from this line of stability, we end up either emitting electrons or absorbing electrons. So the set of these many isotope experiments shows that any displacement from the stable position means either electron emission or electron absorption. So it's a quite straightforward idea that there must be then some negatively charged components to the nucleus.